Okay, so not everyone's back, but that's fine. So this is the last equation we had. This is where we'll begin now. This is where, well, the fun begins, I think. So you see we have some problems here. We have the integrals, or problems, and we have the sums. The rest of this, or also the differentiation. That's what we're going to look at now. Okay, so you might remember from the Gaussian quadrature that when we wanted to integrate function f from -1 to 1, the point was that we should have some weights, w or omega I, and some function evaluations, fx I, for some kind of functions 1 to n 1. Okay? So that's, again, almost the same as a Gaussian quadrature. Only instead of using the Gauss-Legendre points, we're using the GLL points this time. But these omegas are, again, integral of all of these points here. So that's how we can find these omegas, by integrating the polynomials. So these can be pre-computed, meaning that we can do it once for a reference element, and then we can reuse them. Okay, so yeah, that's why you have the reference element. You just do this once for reference element and not for all of the others. For all of the others, you just use a linear transform, which is a very inexpensive operation to do in a computer. It's basically just a linear equation. This, on the other hand, is not a linear equation. Next, we also need to figure out what these things mean. And that's, well, differentiation. So we are looking at dx. So J of x. Okay, so I'm going to use x here because it's easier to write than the xi. But this is valid for both x, xi, g, I don't know, tau, just a symbol. So if we differentiate a function f of x at point I, we get our operator d of I. So this is d here is the differentiation operator. Just similar to as we've had earlier, j equals 1 plus 1, f evaluated at the point f j, x l j j at point xi, and we get some kind of matrix dij. Oh, let's see, I have to sum it, of course. J equals 1, n plus 1, dij, fj. I think here we have interpolated our function f with these basis functions, lj. And then we say that this is a matrix, the dij, and we see that dij is basically just j at the point xi. Okay? So this is going to be sorry, it's annoying with the diagonal matrix. And the way we actually compute it, that no, it's not going to be diagonal, but dij is dj over I based on the points x I minus x j J, and these J S T 0 I is S J, all of the polynomials I. Okay, so it might look advanced, but this is something you only have to do once. So you can pre-compute this differentiation matrix, and then you have it. So this is based on your points. And again, in reference space, that's the only place where you need to do it. So you need to do it once, and then you can reuse this for the rest of the elements using your transforms back again. Okay. So back to this equation. Now we want to approximate these integrals using the same GLL quadrature that we had earlier. Okay? Because now these basis functions, they are defined using the GLL quadrature, and we can also approximate the integrals using this same quadrature. We get stuff for free now. Again. Okay, so if we do approximate this using the GLL quadrature, we will get weak form, one element, approximating integral LL points, which are just picked because they give a lower error. So again, we have some basis functions. One I double dot, and then this integral is exchanged with a sum, a weighted sum. Okay, 1, 1, omega, k, rho, j. Oh, let's do this properly. Okay, because this is part of our function now. Li, ik, lj at ik, x at k. So here, these are points now, case. This is the first one, then we have repeat the rest, unfortunately. So we have, again, one, E, again, the GLL quadrature, 1, weight, k, u at the point by k, then we have these p by k, k, ok, I, Okay. And this is going to be easier in a moment. Just bear with me. Transform squared dx evaluated at the point. Okay, and then this is maybe the easiest element to see. It's k equals 1 plus 1 k l j k k t dx equals psi. Okay. Okay. This is just a slight rewrite of what we had end of last lecture. So give you a couple of minutes and we'll get to some of the nice properties here. So if you remember some properties of polynomials that we had. Okay, because now the polynomials are defined using the GLL quadrature, and we're also doing the integration using the same points. And we have that Li evaluated at point xi of k, this d k, this Dirac delta k, that's either 0 when I k or 1, and 1 when I equals k. Okay? So all of these, they are just 1 when I and k or j and k matches up. So this sum isn't really much of a sum, is it? Folders. See that well, this one is up here, here, and also down there. So let's take just one of them first. This is also one reason to have the Lagrange polynomials. Self. Okay, so I will first just look at this term up here. That is going to be, I'll go through why it becomes this. You still need to sum over all of the test functions. I, E, V, T, then these weights, J, O, J, dx, I, J. You see, we basically just eliminated a sum here. So we get the integral for free almost. Okay. Yes, I should also add I, j. But this is only 1 when I equals j again. Meaning that this, okay, let's just keep it like this. Okay, but you see this is only going to be 1 when I equals j, so this sum kind of goes away. So it's going, so after a while this is going to be a diagonal matrix. Basically used. So if I equals j, then this is just j j j dx. J. Just a number. J. And the same is for this source term. See the source term there, but yeah. So the source term is also going to be, see, omega k 1 j k is f x d omega j f at j t dx I where xi equals j. We are using the property that the Lagrange polynomials of this. So the Lagrange polynomials, they are defined using the GLL points. And we're also doing the integration using the GLL points. And when we evaluate the Lagrange polynomial at point not in itself, then it's 0, so it just disappears. So this, yeah, it's a root right there. It's a root. So we get this property here from it, meaning that all of these integrals, which we approximate using a sum, is not really a sum at all. And we still keep the accuracy we want. This is just this. Okay, so we had the weak solution for one element, and then we approximating the integral using the GLL points. First. Okay. So, and then we're just approximating it, and then we're applying this property. And when applying this property, we get results over here. So this property over here. Oh, I could use the I, that is the IK, the JK, is that what you wanted? Yeah, this is the same as the I. Okay. Because they have to be the same, or else it will be 0. To see here if K isn't, no, K is irrelevant. Yes, yeah. You had a question? Yeah, you look at the evaluation at the roots. Hmm. DLL. Hmm. Hmm. Yeah. Yes, and or it's going to be baked into the solution in a while. If that's a answer. Should I? No, I don't have to. I should also do this. Okay, so what I've done here, I've applied this to the top one and the lower one, but we can't really do that much with the with this one, this term. That's just going to be like it is. But we are going to define. Well, I mean, you can also compute it. So we will end up with colors there. Okay, so we'll define this here as Mij, which will be diagonal because of this. Matrix. And then we have, oops. This. So we are able to evaluate the differentials here using this Dij matrix. Okay, but I would call this monster K J E, no, I for element E for each element. And then the last one, just F the, that's, yeah, this. F J element E. It's okay to take shortcuts like this instead of writing the same over again. Good. Okay, so these are the ones we're interested in now. And now we can create a matrix equation for this. that is going to be 1 plus 1 E J MIJ J and E plus 1 I T K J equals F J. Only there's some nasties hiding in these matrices. And now we have that Mij is going to be diagonal and also trivial to invert for. This one is not going to be diagonal, but not bad. But now we have an equation which is not too bad, which should hold for each of the elements. Yeah. And it's also now easier to find an explicit formula for UI. Well, this double dot here. Okay. Now we have to glue stuff together. So now we have what you were asking about, because now we have the solution for each of the elements. So now we have, for instance, to say we have the stuff going from 1, let's see, 3, 4. So these are all the points. So G1 here and G2 there. These have to be glued together to create this 1, 3, 4, or not divided by, but 2/3, like points. So, okay, so this is just for 2 elements. Next, we need a table to keep track of all of these elements and how to glue them together and actually assemble it. So, let's see. So now we only worked locally on one element. Now we need some kind of global matrix to actually get a solution out of this. And again, it's okay to do in 1D. 2D, you will have boundaries that are, well, bigger, I suppose. So we need to assemble ME AE the global. I'm going to call it G and KG. So the E here stands for element and G stands for global. Hmm? Yes, that's also just for one element, of course. But also it's not a matrix, it's vector. But yes, yeah, of course. So inside this, so you have this matrix here, and inside it you will have some kind of sum here, which you have to split out. Might be skipping a detail. Okay, so now we assemble it, skipping some details there, unfortunately. And using the fact that this global one, it's still going to be diagonal, because, well, it's just made of a bunch of diagonal matrices. We can solve it using something called the Newmark scheme. So solving the global system. So example, this is again just a name. Newmark scheme. So in pseudocode, for I equals 1, well, the time steps in P, same as for solver start, would have that the field equals field itself, the T V or U the dot 1 off squared A probably have initialized these somehow though. Let's say the B and A starts as 0. Well, I do though. Okay, and then we need to compute stress and assemble these global matrices. Global matrices. And then we update A inverse, and this matrix here should be trivial to invert. Old A and V equals dt of A. I know this is skipping a couple of details. To give you a overview. So, last couple of minutes, I can just give you the SEM overflow, and then I won't be covering spectral elements in 2B. I hope that's okay, because that's just a lot of equations. If you want, just send me a message and I can send you the notes. But okay, so let's try to summarize what we're doing in a couple of sentences. So kind of a workflow for spectral elements method. Oop. So our workflow. So first, you have to create the mesh. Problem with this, it can be difficult, and it's its own field of research. If you want a commercially available software for doing all of this, I haven't used it myself, but sol.io. If you go to this website, you will find a finite element solver for the wave equation. They've implemented all of this. It's a fairly new software. It's also expensive, what I've heard, and they implemented all of this. So the mesh, they also do the meshing. So they do the meshing and solving everything in the software. Cool guys to talk with. So that's the meshing, creating the mesh, its own topic of research. We won't be covering it. It's complicated. You could just be stupid and just create a very dense mesh, and then yes, it works, but then you're also using a lot of computational power to solve it. So actually, creating the mesh in an optimal way, that's a problem I won't cover. Okay, this one, and then we're just solving the equation. That's the other one. So solving the equations entails actually in each time test, so we need to update each of the elements based on the global solution. It's information. From the global system and then solve the equation on each element. So this basically means that, yes, you have to update each of the elements, and then you solve each of the elements separately, and then you need to put them back together again. And then you update the local elements, you split them, and then you have to go back and forth with the global and the local one. And in the local scale, you can just use the transformations and reference element to solve it. Only that on the reference element, you have different inputs, which is the field at that global scale and the parameters at the global scale. Then you do a lot of transformation back and forth. But basically, as long as you can solve it for this reference element, you can solve it for the full system. And when you've done this, oh, well, I guess this also. Assemble. Double. System. After doing this, well, then you update each element, solve each element, reassemble. Then do this over again. Reference the element. Okay. So who's going to implement this for the project? Start all over again. You see, it looks like a much more complicated way of actually doing it. So, well, in my research, we actually just use the finite difference methods. They are good enough. But if you want to do seismics on a global scale, then it's also difficult to get the shape of the Earth well properly represented on a square or a box in 3D. So that's why this finite element method is mostly preferred in a global scale seismics and not exploration scales. But it's still a cool concept too. Okay, any questions before we stop? We have one topic left. Is Lattice Boltzmann gases. There's going to be less, well, there's going to be more math there also, but it's the way of implementing it is more based on logic than math. It's a different way of doing simulations than actually solving equations. You're solving logical problems instead. So next week, try to take a look at Conway's Game of Life. See what that's all about. That's something called a cellular automata. So you're starting with a very simple systems and simple rules, and then you can explore this thing called, for instance, Conway's Game of Life, and you will get these intricate patterns and just like dynamical systems going on. People get obsessed with this Conway's Game of Life. I had a face also. Solve it. It's just interesting to take a look at. If you want to test it yourself, there should be some example code of Conway's Game of Life on exercise 0. So try to run that code. Just see what it's all about. So this is the same concept as with this Lattice Boltzmann gases. Okay. Then I suppose have a nice weekend. Only Thursday, but still.